So now you can check, we find out this type of result. This is the latitude, this is the longitude, and this is the mean value for each point. Okay, so now we find out this type of column look like that. Okay, and this information is extract from that your map. This from this map, we extract from this map for this type of point data. This type of point, this type of point, this type of point, we are just extract the data. And this is the way we can apply and extract the point data information for any map. It's very helpful. Suppose when you for the real project, first time we just simply visit the field and extract the data, ground truth data. So this ground truth data further we need to compare with the satellite data. So this type of ground truth CSV information simply import in the Google Earth engine and extract the data for from the Google Earth engine, from the satellite imagery. Further, we just compare this data. Suppose this is my ground station data. I have some nitrogen dioxide data, and now I extract this type of data from satellite imagery or satellite information. Further, from here, I just calculate the accuracy or calculate the regression or calculate the different types of things using the data, ground truth data and also satellite data. And this is the things just we apply and then extract the data for a specific point. So now let's check the one practical example. I will show you that how we can easily use this type of information. Suppose okay, let me check the another data set. So this type of things you can also apply for any other Sentinel-5P. So you can see the Sentinel-5P provided a lot of gases. So you also try same process. Okay, you also try this type of gases at the same process for sulfur dioxide or nitrogen, carbon monoxide, formaldehyde, ozone, or methane. So you also try create the map and also make the time series chart, also extract the information, point data information, same process. So now I talk about that AOD data. AOD data basically aerosol optical depth. I simply search here AOD MODIS. And how we can easily make the linear regression using AOD data and also ground truth data. I also show you this type of example. Suppose if you check, this is the Terra and Aqua land aerosol optical depth data from the MODIS. So this data set, we can easily find out that optical depth information or AOD 0.47 micrometer optical depth information you can easily find out. And this is the daily data. So let's go try to use the data. Same process. Just let me open a new code editor. Okay, so just where is it? I think I remove it. Just a minute. MODIS AOD data. Simply search MODIS AOD. This is the data. So just I import the data from here. So I put the name suppose AOD. AOD data set. So now we just filtered the data. So just take a variable, suppose AOD. You can put any variable name. So just call the AOD data set and select the band. So if you check the band information, aerosol optical depth, I want to use the 0.47 micrometer. This information, just paste. Okay, and now put the filter date. I put here suppose year of 2024 1st January, year of 2024 suppose 31. I take the month of January data. Okay, so now if you check how much image is available for that, so print AOD, use at the size function. This is the total number of images we find out in here. And okay, also import the study area. Suppose I need the data for whole country boundary of Bangladesh, and I put the name as a ROI. And then okay, and if you check the data, this data set, we also need to reproject the scale value. They already provide the scale, you can see 0.01. So when you find out this type of scale value, any data set, try to use it to get the more better pixel. So for we are just use a function in here. So just create a function. Put the element, suppose img, then use it. So I want to return this image, multiply with this value, okay, 0.001, and then these things I want to apply for all of images. Okay, so that user dot copy properties this element and apply system time start to system time end. Okay, so now this is the function and this is the collection. For connecting, just use here the dot map function for connecting. So now it's successfully connecting with the AOD. So now if you want, you can simply make the map of AOD. Just take a variable, suppose I want to calculate the mean AOD using this collection AOD. Just I copy, just use at the mean function for computing the average, and click with our study area, which is ROI. And then we try to add the layer, map.add layer, and apply the mean AOD. I want to just add the visualization and also focus the center of the given study area. Map dot center object is ROI, zoom level 10, and click the run. So now you find out it working. Okay, so now we try to add the visualization. Let me add their color code. Just I copy and paste, and also stress the data. and then check the data. We find out this type of results. Just I copy and then paste and also copy. So we find out the 0.2 micrometer from 1.4 micrometer, this type of aerosol optical depth value. So these things I copy and paste after this name and put the layer name. It's a AOD and run the code. So we find out this type of map. Red is indicating about the high aerosol optical depth, black is low. Okay, so now suppose I have some ground truth data. Ground truth data basically it stored the information for PM 2.5. Okay, because in this case we make the correlation AOD to PM 2.5. Okay, PM 2.5. Simply search on the Google. We find out lot of information about that AOD and PM 2.5. So you can read also scientific paper about that. So if you check it, okay, let me open AOD relationship comparison between the PM 2.5 and AOD. And they are calculate this type of value. If you check it, so a critical assessment of the high resolution aerosol optical depth AOD retrieves from fine particulate matter PM. Okay, so using the AOD data we can easily predict the PM 2.5 or particulate matter. So now in this case we are just apply the ground level PM 2.5 data we need. Okay, ground level PM 2.5 data we need, and we also need the satellite data. So now you can see we already make the satellite data. So this is the satellite data. So now if I have the ground truth data of PM 2.5 for a specific point, then we can easily make the map for PM 2.5. Okay, this is the called the statistical approach for PM 2 AOD to PM 2.5. Okay, so now how I can do? Suppose I have a data. Okay, let me show you that. Where is the data? Where is the data? Okay, let me try to. Suppose this is one kind of data. Okay, suppose if you check here, suppose okay, this thing I already work, so that's why it look like that. So I have ground truth data. So this is the ground truth data for this type of coordinate. Okay, so now from here I just download the data, this type of data from satellite. Okay, suppose this data 4.2 microgram per meter cube, this is the data for PM 2.5, and this data I collect from ground station, this type of latitude longitude value. So now I want to export the data for satellite data from AOD data for the same coordinate. Okay, then further we just make the linear regression about that and predict PM 2.5. So let's go. I will show you the full process how can it work. So this is the data. Okay, this data is stored the PM 2.5, this type of value for this specific geolocation. So now I also want to extract the data, AOD data. Okay, AOD data from satellite, and this data is generated from ground truth data. So they are the different sources. We also find out the PM 2.5 data, as well as we also use the some instrument to identify for PM 2.5 data for any specific geolocation. So now I have this type of data, and this I also need the data for AOD data. So now this file we need to import in Google Earth. I already import a file, you can see. Suppose I use the same data, same point data. Okay, so now just we try to export the AOD data. Okay, this AOD data, it's come from the satellite data, and this PM 2.5 data, it's come from your ground station data. Okay, further we just make the linear regression and then compute the AOD, sorry, PM 2.5, we just compute. So let's go, I will try to show you this process. So same process, I already show you that how we can easily extract the point value. Suppose I use the same code, I try to use the same code, it also reduce our time. Okay, just I copy, just copy. Okay, and then paste here, and also import the, I put the name points. Okay, so now if you want, you also add the layer of all points in your map, points. Okay, so now you can see map.add layer points, just AOD I want to extract from here, mean AOD. So mean AOD, just copy and also extract the information, just change it. Okay, mean AOD, this resolution you can check, this resolution is that 1 kilometer or 1000 meter, and then all of those are the same. I put it's a AOD data. Okay, this is my AOD data. So run the code. Okay, so now from here you can easily download all of point AOD information. Okay, AOD information, simply download, and I already have all of point PM 2.5 data from the ground. Okay, I already have. So now using the AOD data as well as also using the PM 2.5 which I collect from ground truth data, we just create a linear regression. Okay, so let's go, I will show you that how we can easily, you can see it already done. So let me show you the data first. Open in Drive, and then open the recent file. Yeah, this one data, this data, just open. So if you check it, we find out that for this coordinate 0.99, this value for this coordinate, we find out the average value of AOD. Okay, and I already have the value of PM 2.5, I collect it. So further I simply use this code. Okay, just I show you the previous code, it also reduce our time. So just I open in the Google Collaboratory, and further we are just make the correlation and also find out that linear equation y equal to mx plus c. Okay, in this case you can see the data. So this is the PM 2.5 data, basically it's come from ground. This is my latitude longitude data, and this is the mean data which I collect from satellite. Okay, satellite data, basically this data, AOD data. Okay, so just I combine all of data to use in the Google Colab, and this is the Excel file. So now I want to predict y equal to mx plus c. So if you just check the linear equation, so basically linear equation, we find out that y equal to mx plus c. Here y is defined. Okay, just I show the image. So y equal to mx plus b or mx plus c, same. So here y is defined on the x. Okay, so x is independent variable, y is dependent variable. So y equal to mx plus c. So here y is predict, we can easily predict the y using the x and also b plus c, m plus c. So here m is the slope value, okay, slope value, and c is for intercept value. So if I know about the c value and also know about the slope value, mainly slope and intercept value, then I can easily predict the y value. Y basically PM 2.5 in this case. For my case, y is PM 2.5 and x is AOD. I already have x. X is AOD. I already have x. So now if I compute the m value, slope value and intercept value, then I can easily predict the y value using the linear equation. So now we just create this type of equation because I have already x value, x basically AOD data which I generate from satellite, and m and also c value. So now I compute m and c value. Then further in this equation, I just use the equation different x value and also predict the y value for PM 2.5. So for this case, we are just use the code. So first of all, we need to import some important library. So pandas library, then scalar linear model, because in this case we are applying the linear regression. So just put the scalar linear model and also use the matplotlib pyplot as PLT for displaying the chart. So now this is the, just simply upload your PM 2.5 data set. Okay, basically this data set I uploaded in my Google Drive, or you can also upload it in here, just in upload it in your file in here, but it's the one time. But when you upload it in your Google Drive and also copy the path, how I can copy the path? Suppose this is my CSV file. Okay, just click on here and copy the path, and this path simply paste here. Okay, and how I can upload? Very easy, just simply click on here, you can see the upload file, and further simply go to your source file and then upload. Okay, upload. But when you upload it in here, then it will be uploaded for one time. If you refresh it, it will be gone. But when you connect the Google Drive, you can see this is the Google mount drive. So just click on here, then you find out the drive option. So now in your Google Drive, all of file we can easily access from here. All of file we can easily access from here. So further from here, you can simply find your folder and then simply copy the path and then paste here. Okay, so here I already do it. So it is stored the path, and also you can see this is the code to mount the Google Drive. Basically Google Drive connect with your Google Colab. So now we can easily access all of file from the Google Drive in our Google Colab. And then I just simply store it df, basically df and pd, mainly pandas. It's help you to read the CSV file. So just I use the read CSV file function, and then we df. So then you can easily find out this type of data. So this data we find out, this is the column PM 2.5. This is the column for AOD. Okay, so basically we just work with PM 2.5 and AOD, mean AOD, to create the linear regression model. Okay, so let's go. After that, in this case, AOD is the independent, mainly x. AOD mainly x. X is the independent variable, and PM 2.5 it's the dependent variable, basically y. So just we simply separate. Basically we take the column name. So mean column, and this is the column name for PM 2.5 microgram per meter cube. Okay, this two column is simply separate, and it's a independent. So that's why I reshape -1 to -1, and it's a dependent, don't need the reshape, just extract the value. So now further, if you display the AOD, so we can create the 1D array, this type of value. All of value we find out in here, and also PM 2.5 we find out this type of value. Okay, just simply separate. After that, we create the fit the linear regression model. So just I simply take a variable model and call the linear regression. So these things I already imported in my, in here you can see I already imported the linear regression. It's come from the scalar linear model. I put the linear regression already. Just call the linear regression and fit mainly train. Okay, just I train using this two column, AOD column and PM 2.5 column. Okay, further we are just calculating the slope. Basically it's a m value slope, and also calculate the intercept value mainly c value. Okay, so now just use the model. Just I call this model. From this model, if I just use the coefficient function, then we can easily calculate the slope value. And if we are just use the intercept function, this function, then we calculate the intercept value. Further, we are just predict model.predict AOD, and then we are just display this type of chart. So in this chart, we can see it show this type of chart. It show the PM 2.5. This column is the PM 2.5, and this column is for AOD, and it actual value, this type of actual value, and it create the fitted line. Okay, and this line is that y equal to mx plus c. Okay, so here y, you can see it show the slope value, basically m plus c mainly intercept value. Okay, so this value is different on your data set. So for my case, I find out this type of value 30.67 x plus 21.79. So this is the value about that. So now we can also create the equation. So just write the equation PM 2.5 equal to slope value multiply with AOD value and plus intercept value. So now we can easily get this type of equation. You can see 30 plus 67 multiply with AOD plus 21.79. So this is the intercept value we generate. This is the linear equation. Okay, so now from this equation we find out that PM 2.5 equal to this equation. Okay, so here I know the slope value, I know about that intercept value, and I have also AOD data in my map. So basically this map show the AOD data. So now I can easily use this map AOD and also use the intercept value and also use the slope value to compute the map, make the map for PM 2.5. Okay, so let's go and try to use this equation. So now I find out this is the equation and data PM 2.5 and also compare with the data satellite data AOD. So this type of linear equation in the remote sensing we use a lot of application. Not only for that, suppose you want to choose organic carbon in the field, you have some ground truth data. So now you just use this data and also extract the information for organic carbon for the whole land in your agricultural land. So then you also use the linear equation. Not only for that, there is the lot of application for different sector. If you have the ground truth data, then we can easily make the correlation, and further we can easily generate this type of equation. And now if I just use the equation in my code, then we can easily find out the PM 2.5 map. Okay, so let's go. This is the equation. So in this equation, I need AOD. Okay, so basically it's the AOD. Okay, and I already make the AOD. So now if I just simply multiply this value and also add with this value, then we can easily find out the PM 2.5. Okay, because PM 2.5 equal to these things. So now we try to apply, suppose dot multiply with slope value basically 30.67 and add with intercept value which is 21.79, sorry 79. So now if I just use this value and if I run the code, then we can get the result for PM 2.5. And now what the accuracy about that? Okay, after creating the map, I talk about the accuracy, basically correlation. We try to check it. So now this is just the PM 2.5. So this is the way using the aerosol optical depth data, we can easily make the map for PM 2.5. It look like that. We need to change the visualization parameter. So let's go and try to change it. Just click on here and apply the, suppose I keep the 98% stressing. We find out the 27 and then find out the 66. Run the code. So now if you check the value, suppose click on the inspector tab and click, suppose I click on here, so you find out the AOD PM 2.5 value 67.52. Okay, if I click on here, 56.31. And okay, if simply search here, suppose I'll show the real project for the real work, then you also get the more better idea about the. Okay, so let me open. Okay, let me the previous code I just show you that, for example. Okay, so let me show you these things. Suppose, okay, so this, okay, run the code and show you the result. So this is the result. We try to use the whole India country boundary, and we also try to add the health concern. Suppose which place is the good, moderate, unhealthy, very unhealthy, hazardous. Using the PM 2.5, we try to use the data for 2024. Okay, and then we calculate this type of thing. So in this case, we are just apply the same process. First of all, we need to extract the data, some training sample. Okay, then you can say find out this type of equation. For in this case, we find out the equation is that PM 2.5 equal 271.34 multiply with AOD plus 22.24. So this is my linear regression. I generate the same way, just apply the same code and try to calculate this type of equation. So further this equation you just apply in our code, and then we create this type of PM 2.5 map. Okay, and World Health Organization, they also make some classes. Okay, they also make some classes based on PM 2.5 value. Okay, suppose you can see the range less than, greater than 0 and less than equal 50. So this is the range for good. Greater than 51 and less than equal 100, this is the result for moderate. And also for unhealthy, unhealthy for sensitive group, unhealthy, very unhealthy, and hazardous. Okay, they also make some group. So if you read some paper and also search the Google, okay, I'll show you that, just a minute. Suppose AOD to PM 2.5 estimating. Okay, lot of paper also estimating PM 2.5 surface to concentration from AOD. Okay, relationship particulate matter 2.5. Okay, let me check who standard value for PM 2.5. Sorry, PM 2.5. Okay, so if you check it, okay, just open it. So here you can see they are make this type of classification 0 to 50, 51 to 100, 100 to 150, 151 to 200, 200 to 300, 300 up greater than. So they are make some classification range, okay, air quality categories based on the PM 2.5. Okay, the same process we also make the same classification 0 to 50, 51 to 100. Okay, just use the same, and then we try to classify this type of map. So here you can see you find out that this type of value. So this type of green color indicating about that good, then this type of yellow color is the moderate, then you can see this type of color is a hazardous, and this type of red color indicating about the unhealthy. Okay, you can see this type of place we find out that unhealthy for sensitive group. Okay, so this is the overall study we try to focus, and this study will be more accurate when we add the more ground truth data. Okay, so basically it's the linear regression. So just use this code, we try to make the classification, okay, based on the standard value category of who. Okay, so this is the things you also try to apply. Okay, I'll send you all of code, you also try to practice and then do it. But this is the process. First of all, we need to extract the data from ground truth, as well as we need to extract the data from same location data. We need to extract from satellite, further just combine and make the this type of linear equation, and in this equation we are just use and compute the PM 2.5 and create the map. And if you check the correlation, so it's very easy, just call the mean column name and also call the another column name, just use the core function and we find out the 67. Okay, for my data we find out the 67. This correlation value we can also increase if you want to add the more training sample from the ground as a PM 2.5, then this value is also increased. Then we find the Pearson correlation 67. Okay, so this is the whole process how we can easily use the ground truth data and also work with the linear regression, and from the linear regression we generate an equation, further we are just use it and make this type of map. Okay, so this is the PM 2.5 map, further we are just make the classification based on the different types of friends. Okay, anyone in question please? Okay, okay, so now we talk about that how to calculate the total emission. Suppose in month of January, what is the total emission of nitrogen dioxide? Okay, so I use this same code. Suppose this code I want to add. Suppose I want to compute for this year 2024 month of January to December, what the average emission of nitrogen dioxide for this time. So for calculating this type of things, first of all we need to calculate the total emission area. Okay, so let me write the code. Calculate total emitted gas. So let's go try to calculate the total emitted gas. So first of all we need to calculate the total emission area. So for calculating the total emission area, I take a variable, suppose emission area. So this emission area I want to calculate, okay, the total emission area. So for that, write the function e dot image dot pixel area. So it compute the pixel area in square meter unit, and then apply the dot reduce region. I want to calculate the total area. So just use at the reducer. I want to calculate EE dot reducer dot sum. It calculates the total area. Then geometry, it's your shapefile variable name, which is RY. Okay, and then scale. Scale is the resolution of satellite imagery, 1113.2 meter. Okay, and then finally max pixel you also use as a big study area, because otherwise it takes some problem. Max pixel I put the one in 13. So now it computes the total emission area. Just call the emission area these things. And run the code. So now you find out as a dictionary, it computes the total emission area. Okay, this is the total emission area. Unit is the meter. Okay, a square meter. We find out the meter unit. And now I need only for the value. It show the dictionary. So previous class I already show you this code. We need to apply the values function to extract the value, and then we put here the get function, get 0. Okay, so now it extract only for the value, total emission area value. Okay, we find out this total emission area value. If you want, you can also put here number. So put here EE dot number, because further this number we also use and compute the total emission of emitted gases. Just put the E dot and run it. So now it computed as a number object, number computing. Okay, so now you find out the total emission area as a number object. So further this number we also use another equation, and we can easily get the result. Okay, so now we find out the total emission area, and now we need to calculate the per pixel area, how much gas is emitted. Okay, per pixel area. And what is the pixel size? Pixel size 1113.2 meter. So this is the pixel size. So now we computed per pixel area average, how much gas is emitted. So for that, just take a variable. Suppose I put the variable name is that mean NO2 emission, and now just call. I already calculate the average. You can see average map. We already, this is the average concentration map. I just call the mean NO2 and paste here, and apply the reduce region. Okay, and now compute the average. So reducer apply EE dot reducer dot mean, and then geometry is RY, and then scale basically resolution or pixel size 1113.2 meter, and I put the max pixel, suppose max pixels 1E13. Okay, so now I compute averagely per pixel how much gas is emitted. Okay, average value. So now I want to need only for the value, so put here the values function, and I get 0. Okay, so now if I print this mean NO2 and paste here, so now run the code. So now it show the averagely per pixel how much gas is emitted. We find out. And it show the computed object, so we just convert as a number. So put here EE dot number. So now it's computed as a number. So further this number I use for another equation. Okay, run the code. So now if you check it, it show the user memory limit exist. Okay, okay, this it's running, so it's the previous one. Okay, it's working. I think some networking issue. Let me run again. Okay, find out. Okay, so I can see we find out the result 77.52 micromole. So we find out that per pixel area averagely 77.52 micromole gas is emitted. So this result show the per pixel area or per meter square area. Okay, and this is my total area. This is the total area and this is the result for per pixel. So now if you just apply the unitary method, okay, just simply multiply. This is the total area and this is the per pixel area or per meter square area. Averagely, we find out the 77.521 micromole gas is emitted and this is my total area. So now just apply the unitary method to compute the total emission averagely for the whole Bangladesh, the year of 2024, January to December. Okay, so for that, just take a variable. Suppose I put the variable name is that total emission. Just simply multiply. Okay, this is the per meter square area or per pixel area averagely emitted gas value. This value simply multiply with this total emission area. Just copy. Both are the meter unit. Just I paste here and further just print this total emission. Just copy and paste here on the code. So we find out this type of large value. Okay, you can see this is the unit is the micromole and this result for the whole Bangladesh. But how I can do it more better visualization? So this result show the micromole. Okay, this result show the micromole. If I compute the result in ton unit, then it look more better. Okay, if I compute in the ton. So now in this case, we talk about that how we can easily convert the unit ton. Suppose micro mole per meter square to ton unit. Okay, so then we also find out the more better. But in this case, this result show as a micromole because you can see I already write the code data set and put the this value multiply. So that's why this data set is stored at the micromole unit. So now I will show you that how we can easily convert the unit mole to ton. Basically mole to mole per meter square to ton per meter square. Then you also find out that short value. Otherwise you can see if you keep the micromole, it also okay, there is no problem, but it show very long value. Okay, so let's go try to convert the unit mole per meter square to ton per meter square. So this conversion mole per meter square to ton per meter square. So now I need to this data set also need for without I need to compute this data because I already put this value, so that's why it's the micromole, not mole. So just I keep the mole and this mole I convert into micromole. So this is my goal. So let's go. So this is the result. So just I keep only for the without micromole. Okay, if I just multiply then it will be micromole, but now it's the mole and I want to convert mole per meter square to ton per meter square. So this is my ultimate goal. So for that conversion, we know some constant value, know about that. Suppose 1 mole, it's a nitrogen gas, 1 mole NO2, 1 mole NO2 equal, we find out the 46.005 gram. It's a constant value. As well as we know about that 1 pound equal to how much value? Okay, let me check from Google. 1 pound equal to gram. Okay, 453.592. So this is also constant value, it's a gram. So if you just simply conversion factor, just simply divide it to value, conversion factor. So let me divide, just a minute. $453.59 592 divided by 46.00, sorry 46.005 divided by 453.592. So after multiply divided, we find out the value 0.1014. I take it from here. Okay, so find out the value for this value, pound per mole. Okay, this is the conversion factor, just simply divide it. Okay, so after that, okay, so now we need to 1 pound shaman how much ton. Okay, because we convert the ton. So now 1 pound equal to how much ton? 1 pound equal to how much ton? Okay, 1 pound equal to 0.005 ton. This is the constant value. 1 pound equal to 1 pound equal to 0.005 ton. Okay, so now we simply divide it, just apply the unitary method and multiply. Okay, let's go try to multiply this value, copy or multiply. Okay, multiply with 0.1014. Okay, just multiply 0.0005 multiply with 0.11014. So we find out that 0.0000507. This is the value we find out. So now we need to find out that mean reducer factor. Okay, so this mean reducer factor, basically minimum reducer factor, we need to find out minimum reducer factor, and these things we find out from satellite or data catalog paste. Okay, so if you check the data catalog paste, we find out one value, mean reducer factor, for our data set. Okay, just let me check the data set information for nitrogen dioxide sentinel 5p data. Just check it. Sentinel nitrogen dioxide, yeah. So if you check it, it provides that this type of value. So this is the value for mean reducer factor. Again, this is the max reducer factor. So we can easily find out this value for the mean reducer factor or minimum reducer factor, this value. So it also constant value. You can get this value for any other data set. It's also different. So let me try to put in here. So this will find out that catalog paste of this dataset information. So now further simply subtract these two value, 0.00051, 0.00051, and subtract with 0.00. So this value, mean reducer factor value, minus this value. Okay, this value. So we find out 0.00045, or you can also write 46. Okay, because 9, we put the 46 or 45, no problem. So this is the conversion factor. Okay, so now I just use this conversion factor and convert mole to ton. Okay, so I hope you also get the step-by-step calculation how we can calculate and also find out the conversion factor, mole per meter square to ton per meter square. So this is our final output, 0.0046. If I just use it with my all of images, simply multiply, then we find out the result in ton unit. Okay, how much ton gas is emitted. Okay, so let's go try to do it. So now all of this is my micromole. So this is the this is the mole unit. So just I simply use this conversion factor. So just create a function. So just same process, just apply a function, put the element of image, and then return this image, multiply with this conversion factor 0.0046. just I copy and use here, and these things I want to apply all of images. So copy properties, apply this image from system administrator to system int, all of those. System time end. Okay, so and for connecting, just use the map function dot map. So now it's connecting all of images in year of 2024. So now I want to create the map for ton unit. Suppose take a variable, I put it this the ton or ton mean or average ton. So just I call the dataset. So all of ton image, just create the average and clip with my dataset, which is RY. So now display this map dot add layer and call the ton mean. Okay, so just run the code. So now it added the layer in the ton unit map. We find out ton per meter square. So it create, we also add the color. I try to keep the same color, suppose, yeah, this color, a copy and paste here. Okay, it's working. Okay, let me stressing, otherwise show it's a black color. I just stress the data. So now it automatically show you the mean and max sense for ton. So we find out this is the value. I simply change it and also copy and change it. So now run the code. So now it display the result for ton unit, ton per meter square. Oh sorry, just copy and paste after the layer name. I put the layer name, so it's a ton map. Or you can put any name. Just run the code. So now we calculate the ton map. So now from this ton map, we need to calculate per meter square area or per pixel area how much ton gas is emitted. Okay. So for that, we need to simply change in here. Okay, this NO2 mean NO2. I simply put here the ton mean, because I want to compute it per pixel area averagely per pixel area how much ton gas is emitted. Just I change it. Okay, so now it computing in the ton unit. Okay, total emission gas, we find out the ton unit. So run the code, because now it's computed that per meter square how much ton gas is emitted. Okay, so you find out that this is the value 4930.71 ton. Okay, and this is the value per meter square pixel area averagely how much ton gas is emitted. Okay, so this is the way to convert the ton unit, and further averagely per pixel how much ton gas is emitted to be computed. Okay, and then simply multiply with the total area, because this is the this result ton per meter square, and this result for meter square. Okay, just simply apply the unitary method and then simply multiply, then we can easily get the total emission of nitrogen dioxide in ton unit. So this is the result 4930.71 ton. Okay, in year of 2024 whole year. Okay, month is year of 2024. So this is the process, and you can see this is the ton unit, and this is the micromole. This is the ton, this is the micromole. Okay, if you check the value, suppose click on here and click suppose this place. So we find out the 202.40 micromole and 9.31 10 inverse 10, we find out that ton. Okay, ton is a big unit. Okay, so that's why we find out this type of value. And you can see in this time it show this type of place as a black color. Okay, so then you try to change the stressing level and then put the other stressing. Suppose I put here stressing level suppose 90, then check what happened.